Welcome to Easy Statistics. Easy Statistics is designed to provide you with a compact and easy to understand course that focuses on the basic principles of statistical methodology. No prior knowledge is required when following an Easy Statistics course. You do not need to have a background in statistics to follow what's happening here. In fact, the less you know, the more you'll gain from this course. Most important, there are no equations in this course. The emphasis of this course is on understanding statistical concepts intuitively and in a gentle manner. If you want equations, then there are plenty of other courses and textbooks that provide these. Our focus here will be very much on application and interpretation of statistics. I want you to know how to use and how to read statistical results without needing to know the exact underlying mechanics. It's a bit like driving a car. You don't need to know how an engine works to use a car. You do need to know how to steer, accelerate and brake, and this is what I will teach you here for statistics. What is linear regression? Linear regression is the most popular regression method used. Of the linear regression techniques available, ordinary least squares, often abbreviated to OLS, is the most common. We are going to focus on ordinary least squares because it often underpins more sophisticated techniques, and it is by far the most used regression method in the real world. Ordinary least squares is a technique that examines the relationship between one continuous variable and one or more continuous and/or categorical variables. This technique is used in many sciences, including economics, sociology, psychology, geography, and even history. It is often used in business for quantitative analysis and underpins many government reports that perform some kind of policy evaluation. Anyone wishing to delve deeper into regression statistics must have a good foundation understanding of ordinary least squares. What are the main learning outcomes? To learn and understand the basic statistical intuition behind ordinary least squares without needing to know about complicated equations. To be at ease with regression terminology and the assumptions behind ordinary least squares. To be able to comfortably interpret and analyze complicated regression output from ordinary least squares. And finally, to learn some extra tips and tricks that will help you when dealing with ordinary least squares regression models and output. Who is this course for? This course is for academic students of any level. It doesn't matter whether you're studying at school or at university. If you need an easy introduction into linear regression, this course is for you. But this course is also for practitioners, such as business users, including managers who deal with quantitative analysis at their workplace. This course is also for those working in government, especially those who are involved in policy analysis. Finally, this course is aimed at anyone who has an interest in or needs to engage with statistical regression. What prerequisites are needed? You do not need to know about mathematics or statistics to follow or get the most out of this course. Curiosity is all that is needed. Some data knowledge may come in handy for the practical application part of this course, but it is not required. Stata is a statistical software program that allows users to estimate many regression models. I will use it to demonstrate ordinary least squares regression. A keen interest in understanding how measurements might be related to each other. Regression is all about measuring quantitative variables against each other. If you want to know how y is related to x, then this is the right place for you. Using Stata. In this course, I'll be using Stata to demonstrate ordinary least squares regression examples. Stata is a purchasable statistical software, and you can find out more at www.stata.com. There are many courses on how to use Stata should you be interested. In this course, I will not teach Stata, but focus on the interpretation of output. However, if you are interested in Stata and replicating examples from this course, I have attached the relevant do files to this course. Do files are Stata syntax files that contain code that allow you to replicate what you see on screen. We'll be using the auto training dataset that comes inbuilt with Stata for practical examples. This data is a training dataset that contains a variety of useful variables and relationships that are great for teaching purposes. What is regression analysis? Regression analysis is a statistical technique that attempts to explore the relationship between one dependent variable and one or more independent variables. An alternative term used for dependent variable can sometimes be the outcome variable, the response variable, or the endogenous variable. A dependent variable is normally denoted by the symbol y. Alternative terms for independent variables are predictor, explanatory, or exogenous variables. Explanatory variables are normally denoted by the symbol x. It is common to write regression models in the form y equals to x1 plus x2 plus x3, etc. The last term will be an error term. This is often denoted by e. This captures everything that is missing. However, there are many different practices when writing regression models in mathematical form, so we will avoid all of that in this course. Variables can take many different forms in regression analysis. They can be continuous, in other words, data can be measured anywhere on the number line to many decimal points, i.e. minus 2.3 or 500.3. Data can also be in integer format, such as 1, 2, 3, 4, 5, etc. Data can also be in binary format, such as 0 or 1. Often these denote binary responses, such as yes and no. Sometimes data are ordinal. Ordinal data is categorical data that is ranked, such as Likert scales. Finally, data can also be nominal. This is categorical data that is unranked, for example, modes of transport. Importantly, data must always be in numeric format. Mathematics and computer software can do very little with string-type data. String-type data is data that contains letters and other non-numeric characters, like exclamation marks. Data can also be transformed, and this is a common feature of regression models. For example, taking the log of y and making this the new dependent variable is a very common technique in regression analysis. By doing so, the interpretation of the entire model will be changed, and clearly this needs to be carefully considered when using or analyzing such models. What is linear regression? Regression analysis is a catch-all term for every type of regression method. Often regression methods are split into linear and nonlinear regression methods. And there are many methods in both of these two camps. In this course, we'll focus only on linear methods, specifically the ordinary least squares method, that is the most popular linear method. Linear regression assumes that variable parameters relate to the dependent variable in a linear way. Variable parameters are what we try to estimate with regression models, and they define the relationship between x and y. We often call parameters coefficients. For example, a parameter or coefficient of 1 means that for every unit change in x, y, the dependent variable, changes by 1. Without getting too technical,
Linear regression assumes that dependent variables are measured as continuous variables. Explanatory variables can be measured in any way. When the dependent variable is non-continuous, the correct regression method is often non-linear. However, there are instances where linear methods can be used when the dependent variable is not continuous. When there's only one explanatory variable in the model, in other words, there is only one x variable, we call this simple regression. When there are multiple explanatory variables, we call this multiple regression. Most regressions are of the multiple kind, as in practice, we usually want to test or evaluate many variables against a dependent variable y. Why is regression analysis useful? Regression analysis is useful for when quantitative evidence is needed to answer a particular question. Quantitative analysis, by definition, requires the analysis of numbers. The opposite of this is a qualitative analysis, which analyzes non-numeric data such as word, stories, meaning, or concepts. Regression analysis is useful because it allows for the testing of hypotheses. For example, do men really earn more than women? Is unemployment in the economy related to inflation? Or how much more ice cream is bought on sunny days? These kind of questions can be answered with statistics, and you'll often hear the term "this is statistically significant at the 5% level" in such analysis. However, regression also allows for predictions. Because regression models estimate parameters or coefficients, these parameters can then be used to compute new statistics. This can be done within a data sample and even outside a data sample. For example, after a regression of various explanatory factors on wages, we can use the estimated parameters to compute the expected wage of a very particular type of person, whether they are in the sample or not. This prediction is a great strength of regression methods, and it allows businesses, researchers, and policymakers to compute various effects. What type of regression analyses exist? There are many. Too many to count. In fact, many advanced regression methods will be customized for the relevant research question and the data. However, there are some core methods that you should be aware of. These methods are primarily a function of the nature of the data and the nature of the dependent variable. The most common method is ordinary least squares. This method requires the dependent variable to be continuous and is often applied to cross-sectional data. Cross-sectional data is data that doesn't have repeated time elements within it. Ordinary squares also serves as the basis for many advanced methods such as weighted least squares. Next are three nonlinear methods. These methods are nonlinear because a dependent variable is not continuous anymore. Logit and probit models are useful for binary dependent variables. Ordered logit and ordered probit models are useful for when there are multiple ordered categories in the dependent variable. And multinomial logit models are useful when there are nominal, i.e. unordered, categories in the dependent variable. If you're wondering what logit and probit models are, these are simply two common ways to achieve a nonlinear relationship between the variables. Whilst there are some mathematical differences between logit and probit models, in reality these often make little difference to the results. Also note that multinomial probit models also exist, but they are not frequently used, which is why I'm not listing them here. Next are panel models, both linear and nonlinear models. There are many methods in each category, but the common feature is that they all work with data that is collected repeatedly over time. This could be short household panels or long, high-frequency trading time series. Next are count data models, which are similar to logit and probit models, but use slightly different transformations to account for count properties in the data. Examples of counts are things like the number of doctor visits or the number of t-shirts sold. Finally, Cox proportional hazard models are often used when a dependent variable is time. A common example of a time-dependent variable is survival time of cancer patients, and this method is often used in the health sciences. Explaining regression. Now that we have some basic understanding of the concepts behind regression analysis, and also what type of regressions there are, let's explore how it actually works. If you're an academic student, regression is often learned through a variety of equations, often matrix type equations that have a lot of x's and y's and e's and u's in them. They serve their purpose, but you don't actually need to understand them to learn how regression works. Using visual aids can achieve the same effect, and this is something we'll focus on in this course. Simple linear regression is often explained through correlation. So let's follow that approach and then slowly keep building things up later. Correlation, sometimes called association or dependence, is the relationship between two things. In statistics, these things are often variables. Let's call them x and y for now. Note that both variables x and y are connected to an identifier. Without this identifier, none of this will work. The identifier is often represented via the symbol I, and we can imagine it to be something like individual people, or firms, or countries, or anything else that can connect the two variables of interest. In this little table over here, there are three identifiers, and each identifier has one value of y and one value of x. Let's go ahead and visualize a larger version of this table on a graph. I'm going to plot 100 data points on a scatter plot where the y-axis represents the variable y and the x-axis represents the variable x. This visual representation is slowly starting to tell us something. In this case, we seem to get a fairly good idea that there seems to be a positive relationship between y and x. In other words, as x increases, so does y. However, there's also some noise in the data, and there seems to be some clumping in the values of y and x around 0. The relationship between the two variables can also change. For example, the relationship could become weaker or even negative. Here we see an example of how data can change its relationship with each other. The correlation between y and x becomes weaker, going all the way to no correlation and then becoming negative. We end up with a relationship that is almost the opposite of what we started with. Visually, it is quite easy to distinguish between extreme type of relationships. However, it can be more difficult to visually identify differences between only minor relationship changes. Take a look at this example. Here is some data that is correlated in different ways. It is easy to tell a +1 correlation apart from a -1 correlation. However, this task becomes more difficult for smaller correlation changes. At first glance, it would probably be quite hard to identify any difference between the first two graphs, even though their correlation is different. One has to look quite closely to identify that the relationship between y and x has flattened off a little bit in the second graph. This becomes especially tricky if there are lots of data. If we had a million data points, then all we would see, for example, is a giant blob of blue. And that is why we often want to summarize the relationship between y and x via some kind of data reduction process. Lines of best fit. What are they and how do they work? A key thing to understand before jumping into the concept of how to produce lines of best fit is that there are two methods that we can use. These are parametric and non-parametric methods. Parametric methods are methods that apply some kind of parameter or many parameters to data. Parametric methods are methods that apply some kind of parameter or many parameters to data. Often the parameters will be in the form of an equation such as y equals to 1x, where the parameter in this case is 1. This method is the method that is used in regression analysis and in ordinary least squares, and has the advantage of simplicity and working with high dimensional data. A disadvantage is that it requires stronger assumptions about the data, and when these assumptions are not met, your analysis might be completely wrong, and often you may not even know about it. Non-parametric methods let the data speak for themselves. The advantage is that you need to make less assumptions about the initial relationships in the data. A big disadvantage is that this method is not very transposable. In other words, you cannot easily tell other people about it. In addition, it becomes extremely hard to operate this kind of method in multidimensional environments. So we often use non-parametric methods to explore basic relationships between y and x, and parametric methods to explore more complicated relationships between y and x1 and x2 and x3, etc. Let's have a look to see what I mean by all of this. Let's start with a scatter plot of some new data. In this case, let's plot data from the Stata Auto dataset and try to figure out how the price of cars is related to the miles per gallon of petrol consumed by individual cars. The initial scatter plot here tells us there is some kind of relationship between a car's price and its miles per gallon. It looks negative, in other words, downward sloping. Now let's try to estimate what kind of relationship this is exactly. We'll begin with a non-parametric method. Like regression, there are many non-parametric methods. So let's pick one called local polynomial regression. Local polynomial regression is a form of moving regression. The user defines a bandwidth, or lets the computer choose one, and a regression is then estimated within that bandwidth. The band then moves continuously across the x-axis step by step and repeats this analysis. The individual steps are then all stitched together to reveal what is essentially a moving average plot of the data. Let's see how this works in practice. The non-parametric method shown here slowly moves across the data space and continuously updates the relationship between y and x. We see that the relationship between y and x starts negatively, but it ends up being slightly more horizontal. In other words, the relationship between y and x here does not appear to be entirely linear. A big advantage of this method is that it lets the data speak for itself and doesn't rely on specific functions or even theory to fit the data. One disadvantage of this method is that the relationship still needs some kind of input. In this case, it requires the size of the bandwidth. If we change the bandwidth to something smaller, the relationship will look different. Here's an example of that. Another disadvantage of this method is that it is difficult to transfer this relationship to other users. How can we explain this squiggly line to somebody else? So we often choose a parametric relationship. A parametric relationship is one that can be defined by some kind of equation. For example, a linear line fitted through the data will have a gradient, and that gradient will be the parameter defining the relationship between y and x. Let's plot a linear function through the data and see how this looks. Here we see a linear line being fitted through the data. In this case, the line fit is based on minimizing the overall distance between the fitted line and all the available data points. This concept is known as least squares, and we'll explore this in more detail in the next session. It underpins the ordinary least squares regression methodology. The fitted line in this case has a particular slope of minus 238. In other words, for every 1 unit increase in miles per gallon, the average car price appears to drop by $238. Great! However, parametric lines of best fit don't always need to be linear. We can also add a quadratic line of best fit. In this case, we recover two parameters that define the relationship between y and x. Here's an example of that. In this case, the relationship between y and x is parameterized by one parameter pulling y down as x increases and another parameter pulling y back up as x increases. In this case, the parameters are approximately minus 1200 for every increase in x and plus 20 for every increase in x squared. Don't worry about the x squared right now, we'll explore this later. But the important concept is that the functional form of parametric lines of best fit can be made to be very flexible, as long as enough parameters are available. So how does all of this relate to regression? Well, this is regression. Specifically, this is simple regression, where y is regressed against one variable x. How about multiple linear regression? Multiple linear regression is an extension of simple linear regression, and it adds more variables to the mathematical framework. One easy way to visualize this is by adding further dimensions to the scatter plot, where each extra dimension represents an additional variable. Let's say, for example, that we wanted to explore the impact of miles per gallon on car price, but controlling for a car's weight. Heavier cars are likely to have poorer miles per gallon, and this may affect their price. Visually, we can represent this by a three-dimensional scatter plot that plots price against miles per gallon against weight. It would look a little bit like so. Moreover, by rotating the scatter plot, we can look at the relationship that each explanatory variable has with y and even examine how the explanatory variables are correlated with each other. Finally, what multiple regression analysis does is, instead of estimating a line of best fit through the data, it fits a plane of best fit through the data. This can be hard to visualize on a screen, but here is a crude attempt of mine. The left graphs show the actual data points on a 3D scatter plot, while the right graphs show the estimated relationship between these data points. This relationship is represented by a 3D plane. If more variables are added to the framework, the plane of best fit becomes a hyperplane of best fit. And this is why we sometimes hear people talking about multidimensionality when referring to regression analysis. Causality versus correlation. Hopefully, the previous examples will have given you a good intuitive grasp of what regression analysis tries to do. There are lots of statistics and maths in each type of analysis, but the underlying concept will always remain the same. Regression analysis tries to tell users how data is related to each other in a way that is easier to understand than looking at the raw data points. However, it is important to be keenly aware of the concept of causality versus correlation. Every regression method is a statistical method that correlates data. That's it. A computer or a mathematical equation cannot identify what is causal. Causality is always interpreted by the end user, and some models allow better claims on causality than others. Evidence obtained from regression analysis about a strong and statistically significant relationship between two variables may be attributed to causality through a compelling theoretical framework and common sense. This can take a lot of practice and almost becomes an art form. Sometimes the data helps. For example, if yesterday's events are used to explain today's actions, the time element in the analysis can be used to make better causal inference. However, in other settings, such as cross-sectional survey settings, it can become much harder to attribute causality. Are people happy because they are healthy? Or are people healthy because they're happy? These are tough questions to answer and require theoretical and philosophical reasoning in addition to statistics. So, you should always be careful when dealing with regression analysis. What is ordinary least squares? Ordinary least squares is a regression method that is based on the concept of least squares. Least squares is a statistical method that fits a line or plane or hyperplane of best fit by minimizing the sum of squared residuals between the line of best fit and the actual data points. We square these so-called residuals because the sum of them is exactly zero when they're not squared. Therefore, negative and positive residuals above and below the line of best fit cancel each other out. Squaring solves this problem. Many other ways of fitting a line of best fit exist. One example is to fit a line via the method of least absolute deviations, where instead of squaring residuals, the absolute value of them is taken. In other words, negatives are turned positive. However, least squares is by far the most popular method across all the sciences. Ordinary least squares visually to understand it better. Imagine a small data set with a few data points, a little bit like this one. Ordinary least squares will fit a line through these data points. This line may be linear, but it can also be non-linear. Let's go with a linear example. The red line represents the line of best fit estimated by ordinary least squares mechanics. In this case, the line of best fit can be represented by a single slope parameter called beta. We often use the Greek letter beta to denote the slope of a regression line. This slope informs us of the estimated relationship between y and x. In this case, y is the price of a car and x is the mileage in miles per gallon. The slope is negative, which means that as the miles per gallon increases, the price of cars decrease. However, note that our slope does not hit any of the actual data points. That is because we are estimating an average relationship between all the available data points. The actual data points are often called observed data points. In other words, y observed. The predicted value of y at any given value of x is then given by the line of best fit. These are called predicted data points, or y predicted. The difference between the observed value and the predicted value is called the residual value. This is what ordinary least squares tries to minimize. You can see here that there are 3 data points, and therefore 3 different residuals. The sum of all 3 is the smallest value that we can achieve in this case. If we change the line of best fit, for example, by moving the line of best fit down, the total sum of the residuals will increase. This is a graphical explanation of what ordinary least squares tries to do. It finds a regression slope and an intercept that leads to the very best minimum sum of residuals. Let's have another look at this with more data. In this example, we're going to use the full auto training data to see what happens to the root mean squared error when we apply different regression slopes to the data. In the left panel, we observe the regression slope going through the data. We'll start with a positive slope of plus 100. On the right panel, we see the size of the individual residuals. The residuals are squared and then square rooted to ensure only positive values remain. The lowest value a residual can have, therefore, is 0. Higher residual values mean that the relevant data point is far from the actual regression line. The average of all these residuals is called the root mean squared error of the residuals, and this is depicted by the red line. It tells us how far, on average, the data points are from the regression line. Now, let's look and see what happens when we change the slope. We can see that as we slowly change the slope of the regression line from positive values to negative values, the average error between the line and the data point decreases. The residuals, on average, are trending down as we decrease the slope. This keeps happening until, after a certain slope value, the average of the residuals starts to increase again. At a slope of around minus 230, the average error from our line of best fit is minimized, and therefore that is our line of best fit. Of course, this graph is a simplified version of what happens. Regression models can have many more variables and therefore many more parameters, and we would need many more dimensions to display such models graphically. Now let's take a look at how ordinary least squares models are often presented by a computer. Here's an example of how Stata presents regression output. Other computer programs may present this differently, but the essence of the information displayed will be similar among all programs. Often, part of the regression output displayed will be diagnostic information that provides high-level information about the overall regression model. In Stata, this is usually the top part of the output. The lower part of the output table normally presents the estimated coefficients for the relevant variables. There are many pieces of information in this table. However, generally, 3 pieces matter most. The first is the actual parameter estimates. In other words, the estimated slopes or coefficients of lines or planes of best fit through the relevant data. In Stata, this is called coev, which is short for coefficient. Each explanatory variable has a relationship with the dependent variable, in this case, price. Each explanatory variable is also conditional on each other. In other words, the effect of miles per gallon, conditional on controlling for weight, is that for each increase by 1 unit of miles per gallon, price drops by $49. The effect of weight is as follows. Conditional on miles per gallon, an increase in 1 unit of weight leads to a price increase of $1.7. The final variable is a constant. Constants are the value that the dependent variable, in this case price, takes when everything in the model is set to 0. In other words, at a weight of 0 and at 0 miles per gallon, a car should cost around $1,946 according to this model. Constants sometimes make sense, and sometimes they don't. In this case, it doesn't make a lot of sense because cars would never have a weight of 0 or consume 0 miles per gallon. Some people say that constants should be removed from models, especially when they don't make sense. I think that is wrong. You just need to take care when interpreting constants. Often, constants should not be interpreted but left in the model. The next most important piece of information comes from the column called STD error, which is short for standard error. The standard error statistic is a statistic that reveals with what degree of accuracy the slope coefficient is estimated. If the standard error is low relative to the coefficient, then we can be more certain that the estimated coefficient is close to the true population parameter. If the standard error is high, we can be less certain and have more noise around our estimate. The standard error is important because it allows us to determine to what extent the estimated coefficients from the regression model are statistically significant. The 4 remaining columns in the results output are all further computations of the standard error and are simply different ways to identify significance. The t-statistic, the p-value, the lower and upper confidence intervals are essentially all the same thing and are based purely on recalculations of the standard error. We'll look at what they mean in a moment. Finally, the third piece of information that matters most is something called R-squared. This information is given in the diagnostic parts of the output table and can be found here. R-squared is a common indicator of goodness of fit for ordinary least squares regression models. It is bounded between 0 and 1, and higher values indicate that the model better fits the data. However, many professional users will caution against an over-interpretation of R-squared statistics. Numbers are relative to the discipline. If you are working with behavioral data, such as people and their choices, then R-squareds of 0.2 or 0.3 are very common and usually indicate good fitting models. If you are working with time series data, such as macroeconomic GDP measures, then R squares of 0.8 or 0.9 are very common and indicate good fitting models. Finally, let's talk a little bit more about how the estimated coefficients are related to statistical significance. Let's begin with the t-statistic. This statistic is an indicator of statistical significance, and normally we are looking for a value of 1.96 or above when we're using a reasonably sized sample. Reasonably sized samples means around 100 or more observations in the model. The t-statistic is easily computed by dividing the estimated coefficient value by the estimated standard error value. Note that when the coefficient is negative, Stata will produce a negative t-statistic. The sign on the t-statistic should, however, be ignored. Next to that is something called the p-value. This is short for probability value and indicates the probability of obtaining the observed result of a test, assuming that the null hypothesis is correct. The null hypothesis in regression tables is normally that a specific result is not different from 0. In other words, small p-values mean that there is stronger evidence in favor of the alternative hypothesis. The alternative hypothesis being that the coefficient is the actual estimated coefficient. In layman terms, a number of 0.05 or below indicates statistical significance at the 95% level. Numbers below 0.01 indicate significance at the 99% level, and so forth. Next are confidence intervals. There is an upper and lower confidence interval. Upper and lower confidence intervals are computed by adding or subtracting 1.96 times the standard error from the estimated coefficient. In other words, the confidence interval is usually 2 standard errors away from the coefficient estimate. Confidence intervals are really useful because they allow you to quickly eyeball statistical tests. Any number outside the confidence interval range will be statistically significantly different from the coefficient estimate. In this example, miles per gallon is not statistically significantly different from 0 because 0 is within the confidence interval range. However, miles per gallon is different from minus 500 because this number is outside the confidence interval range. This can be a really useful way to quickly perform statistical testing, and all it involves is multiplying the standard error by approximately 2. Sum of squares. Now let's take a look at the sum of squares in a bit more detail. The previous regression table also provided diagnostic information on the explained sum of squares, the residual sum of squares, and the total sum of squares. These values indicate how much variation is explained by the fitted model, how much variation is unexplained by the model, and how much total variation there is in the data. By comparing the proportion of explained sum of squares to the total sum of squares, we can produce something called the coefficient of determination, often called R squared. R squared. The R squared value is a widely used measure of fit for ordinary least squares models, and the value indicates how well the model fits the data. Values of 1 mean a perfect fit. Values of 0 mean a terrible fit. However, the basic R squared can only increase as more explanatory variables are added to the model. In other words, models with hundreds of random covariates can saturate the data and produce artificially high goodness of fit statistics. This is why we often also report the adjusted R squared, which imposes penalties to more variables being added to models. If additional variables are not statistically significant, they will reduce the adjusted R squared value. This statistic
tries to strike a balance between rewarding good model building and overloading models with unnecessary variables. However, it should be noted that R-squareds can be easily abused and should be treated with caution. High R-squares do not necessarily imply that one model is more valid than another. Let's take a look at this example. In this demonstration, I'm going to change the noise level around the line of best fit. The true relationship between y and x is 1, and this is what is estimated by the line of best fit. The original data has very little noise, and the regression line hits almost every data point, resulting in an R-squared of 1. Now let's go ahead and change this noise level around the true regression line. We can see that the R-squared changes quickly as we increase the noise around the data. The R-square quickly drops in value, suggesting that the model fits the data worse and worse. However, the model actually remains the same. What is changing is only the noise around the data. Noisier data result in a lower R-squared value, and the layman observer might claim this to be a poor model. But as you can see, the relationship between y and x hasn't changed at all, and the model continues to recover with the correct coefficient value. Both models in this case have the same validity, even though they have different R-squared values. And that is why one should always be careful with R-squareds. The R-squared example leads us to our next discussion point. Best linear unbiased estimator. Ordinary squares is said to be the best linear unbiased estimator if certain conditions are true. Having an understanding of these conditions is important as some matter more than others. These conditions are often called the Gauss-Markov assumptions and refer to 4 particular assumptions that need to be made about the data. If these assumptions are met, then the ordinary squares estimator is said to be unbiased. In other words, the results produced by the estimator will, on average, be correct. If the Gauss-Markov assumptions are met, the OLS estimator will also be the best estimator. Best is another word for efficiency in statistics, and this simply means that the ordinary squares estimator will produce the most accurate results with the least amount of noise. Let's explore these two concepts a little further before we discuss the actual assumptions. Efficiency refers to the width of the sampling distribution, and when an estimator is said to be most efficient, its sampling distribution is less than that of any other estimator. We can visualize this in an easy way by assuming we have 2 different estimators and an infinite amount of data. From this infinite amount of data, let's go ahead and select a small sample and then try to estimate a particular coefficient for a variable. We're going to use an inefficient estimator and an efficient estimator. We're going to set the true value of the coefficient to 1. The first time we estimate the coefficient using both estimators, we return a value of around -6 for the inefficient estimator and -2 for the efficient estimator. Now let's go ahead and repeat this process. The second time, our estimates are closer. The inefficient estimator predicts a value of around -1 and the efficient estimator of around 0. Both are still some way off the true value, but the efficient estimator seems to be getting closer. Now let's go ahead and repeat this process quickly, hundreds of times, and see what happens. Both estimators, on average, get the correct value of 1. However, the inefficient estimator is on average further away with its predictions than the efficient estimator. This is the concept of efficiency, and whilst we normally don't have an infinite amount of data, this concept is often visible in the standard errors of real-life results. Inefficient estimators tend to have high standard errors, resulting in more uncertainty around the true estimated value. Next, let's explore the concept of unbiasedness. When an estimator is said to be unbiased, this means that the mean sampling distribution of the coefficient estimates will approximate the true population coefficient. We can visualize this in an easy way by, again, assuming that we have 2 different estimators and an infinite amount of data. We'll select a small sample of this data and try to estimate a particular coefficient. The true value of this coefficient is set to 1, and this is denoted by the dotted red line. We'll use a biased and an unbiased estimator to estimate the same coefficient. The first pass produces an estimate of around 0 for the biased estimator and 1.5 for the unbiased estimator. Now let's do it again. On the second pass, the biased estimator performs better with a result of 3 compared to the unbiased estimator with a result of 5. But let's continue and repeat this process many times. As we repeat the process, we see that on average, the unbiased estimator starts to predict a value of 1, whilst the unbiased estimator predicts a value of -1. That can obviously be a big problem. For example, the objective might be to perform a policy evaluation, and a biased estimator estimates the policy to have a negative effect, whilst in reality it might actually have positive effects. Bias is a serious problem in econometrics, and ordinary least squares require some pretty strict assumptions for estimates to be unbiased. It is important then to have some understanding of the assumptions behind ordinary least squares. Gauss-Markov assumptions. The Gauss-Markov assumptions are the underlying assumptions that make ordinary least squares the most efficient and unbiased estimator. Generally, 4 major conditions are needed to achieve this result. These are the homoscedasticity assumption, the no perfect collinearity assumption, the linear in-parameter assumption, and the zero conditional mean, sometimes called exogeneity assumption. Roughly speaking, the first 2 relate to efficiency, whilst the last 2 relate to bias. Let's explain each in turn and try to determine which matters most. The homoscedasticity assumption. This assumption states that the variance of residuals remains stable across the spectrum of independent variables. In other words, the errors produced by a variable remain roughly constant whenever we look at a small part of that variable. Failure of this assumption leads to bias standard errors, and this means we cannot rely on hypothesis testing. However, many modern statistical packages can easily test and correct for this assumption. It is very common, for example, to use something called robust standard errors, which increase the inefficiency of the estimates slightly, but make them immune to the failure of this assumption. Let's go ahead and look at an example. In this video, there are 2 graphs. The left graph shows the relationship between the explanatory variable x and the dependent variable y. The overall relationship never changes, but the variance across x will. In the right graph, we see the residuals or errors of x. It shows the distance of the actual data points to the line of best fit. The left graph also shows the slope estimate and the standard error from a normal ordinary least squares regression and a robust ordinary least squares regression. Now let's go ahead and run this example and examine what happens when we introduce a changing variance across x. We see that as we increase the variance across x, the actual regression coefficient never changes. However, the standard errors increase as we increase the variance across x. Moreover, the robust standard errors increase by a little bit more. All this means is that a failure of the homoscedasticity assumption leads to less precise estimates. In the real world, with modern datasets, a failure of this assumption often has little overall effect on the actual results, and most practitioners do not focus on this assumption a lot. No perfect collinearity. This assumption states that an explanatory variable cannot be an exact linear combination of another explanatory variable. If this is the case, ordinary least squares simply cannot be estimated. This is rarely a problem in real life, as you would never enter the same variable twice into a regression. However, when there is partial correlation between two variables, in other words, they measure the same thing to some extent, then we term this multicollinearity, and this can have some effect on our estimates. Specifically, it will increase the noise and therefore the standard errors of our estimates. This phenomenon is generally easy to test for and also easy to deal with by either excluding variables or transforming them. Let's look at an example. In this example, I generated a dataset that has 5 different explanatory variables. These range from x1 to x5. Each x variable has a coefficient of 1. The graph on the right presents the estimates from an ordinary least squares regression and the associated 95% confidence interval around these estimates. We can see that ordinary least squares estimates a value of approximately 1 for each of the 5 variables. On the left graph, we see the correlation between x1 and x2. Currently, there is no correlation between both variables, which is why the data points are scattered randomly. Let's go ahead and see what happens when we start to introduce a correlation between x1 and x2 and slowly force x1 and x2 to measure the same thing. At first, not much happens, but then, as the correlation between the two variables increases, the standard error and therefore confidence intervals of both x1 and x2 starts to increase. This happens until they explode towards the end. This is the effect of collinearity. High collinearity between variables leads to very noisy estimates. But as you see, the noise explosion only happens towards the very end, and in most real scenarios, the effects of collinearity are hardly noticeable. The next assumption is that the model is linear in parameters. This assumption means that the relationship between y and the x's in the ordinary least squares model is linear. In other words, the coefficient estimates take single values and can only be added or subtracted. They cannot be exponentiated, divided, or multiplied. In general, this assumption makes ordinary least squares regression models easier to interpret. Note, this only applies to the actual coefficients. Variables can be transformed in any way, including nonlinear ways. We often call this functional form, and we can vary the functional form as we please in ordinary least squares regression. For example, it is common to add higher order polynomials of variables to a regression equation. A commonly used example is h and h squared, where both variables are entered separately. This has the effect of introducing a curve into the line of best fit. Variables can also be interacted with each other, and we call this interaction effects. This means that lines of best fit can take on very complicated functional forms. Let's go ahead and look at an example. In this example, there are two graphs. The left-hand side shows a data plot of the auto data, where the price of cars is plotted against miles per gallon. The right-hand graph shows the residuals, or how far the individual data points are from the line of best fit. The average distance is represented by the red horizontal line. The initial relationship plotted through the data is linear, but it should be fairly obvious that this relationship is probably not a good fit. So let's introduce a quadratic into this relationship and slowly increase the coefficient on the quadratic term from 0. Here's what happens. The line of best fit starts to curve upwards. This curve results in a better fit, and we can see the residuals coming down, especially for higher values of miles per gallon. Our model fit improves. At some point, we overfit the model by continuously increasing the quadratic coefficient, and the model fit becomes worse again. This example highlights the power of functional form. The model is still linear in parameters because the two estimated coefficients are only added or subtracted, but the square manipulation of x leads to a complicated nonlinear functional form that improves the model fit. Zero conditional mean. Often called the exogeneity assumption, this assumption is one of the most important assumptions in ordinary least squares. The assumption states that there is no correlation between an explanatory variable x and the error term. Failure of this assumption leads to bias in the coefficient estimate. This assumption can often fail in real life, and because it involves the error term, which by definition is not observable, can never be tested. A good rule of thumb is that whenever a variable is a choice, especially an individual choice, then it's likely to be driven by factors that are unobserved, and hence a relationship with the error term might exist. Let's have a look at an example. In this example, I've set up a simulated dataset that again contains 5 explanatory variables. Each variable has a coefficient of 1 in relation to y, the dependent variable. On the right-hand graph, we can see the individual ordinary least squares estimates and associated confidence interval for each of the 5 variables. The correct results are shown by the vertical red line. On the left graph, we see the correlation that the variable x1 has with the error term. Note, in reality, we can never observe this as the error term will always be hidden from us. Only in this simulated example can we see the error term. The original correlation between x1 and the error term is set to around 0. Now let's go ahead and increase the correlation between x1 and the error term and see what happens. We observe that the ordinary least squares estimate for x1 slowly deviates to the right, away from its true value. The more we increase the correlation between x1 and the error term, the higher the bias in our result becomes. This can be a real problem in applied work. And when we have such a problem, we often call it endogeneity. How to test and correct for endogeneity? It is not possible to test for something that cannot be seen. That is why good ordinary least squares models are strongly underpinned by theoretical frameworks, prior literature, and rational argumentation. This assumption is also why many scientists argue against data mining with ordinary squares models. Data mining approaches increase the likelihood of the exogeneity condition failing and results becoming biased. In the real world, the way to deal with endogeneity is often via more data, better, more thoughtful model building, different functional forms, and also sometimes simply accepting that the models may have some bias. Let's recap the Gauss-Markov assumptions. The linear and parameters assumption is a condition that requires all betas to be additive. It means, in layman terms, that the dependent variables should be continuous, but it does not mean that the relationship between y and x must be linear. More complicated functional forms can be worked into ordinary squares regression models. Violation of the zero conditional mean assumption, often called the exogeneity assumption, can lead to biased estimates. This is a very important assumption. It is not possible to test for it statistically, and identifying or defending against it must be done on theoretical grounds. There is no easy solution if this assumption is violated. Options are to include missing variables in the regression model, to attempt alternative identification techniques, or to resort to simulation-type methods that try to identify the size and direction of any potential bias. The no perfect collinearity assumption must be met or ordinary squares regression won't work. However, weaker collinearity between variables will result in increased standard errors. Fortunately, standard errors only explode near extreme correlations, and this can be tested for and corrected by either dropping variables or transforming them. Violation of the homoscedasticity assumption leads to incorrect standard errors. It is easy to test for using an appropriate statistical test and easy to correct for with robust standard errors that are included in almost all statistical software packages. Let's explore some of these concepts we've been discussing in a more applied environment. We are now in Stata, which is a statistical software package commonly used to analyze quantitative datasets. It's similar to other packages such as SPSS, R, or SAS. I won't explain how to operate Stata or the code that I'm executing to obtain the results. You can learn more about Stata in specific Stata courses. I've already opened up a training dataset called Auto. Let's go ahead and examine it a little bit closer before we start running regressions. A common mistake is to start analyzing data too quickly before fully understanding what's actually inside the data. Modern datasets can be very complex, and more often the time spent on data preparation and manipulation will outweigh the time spent on actual regression analysis. Let's describe the data to see what we have. The output returned by the scribe will produce some high-level information about the data, such as where it is located, how many observations, and how many variables are included. In this case, our data contains 74 observations and 12 variables, so it's not very big. It also has a title that tells us that this data is related to cars from 1978. Below that is information about the variables. One of them is a string variable that contains the names of the car types, and the rest are all numeric variables. Let's pretend that we are really interested in explaining the determinants of car price. We can already start building a picture in our head what variables might be important in explaining the price of a car. Weight and mileage seem like important variables, whilst turning circle is probably less important to most people who buy cars. Next, let's explore some summary statistics of the data so that we get some idea of how the variables are measured and distributed.
price appears to be measured in dollars, and the least expensive car costs around $3,000, whilst the most expensive car costs around $16,000. Such prices seem reasonable for 1978. We also see that the variable Rep78 has some missing observations. It only has 69 instead of 74. Most variables also appear to be continuously measured. However, it looks like the variable foreign is measured as a binary variable. Let's go ahead and confirm this quickly. By tabulating foreign, we see that indeed foreign is measured as a binary variable. Around 29% of cars are foreign. So let's go ahead and estimate some ordinary least squares regression models. Rather than immediately going into a full-blown model with many variables and interaction terms, let's build it up slowly and interpret the output and diagnostics along each step. The variable foreign leads itself to a nice simple question. Are foreign cars more expensive than domestic cars? We could answer this question by more expensive than domestic cars. We could answer this question by same thing in a regression framework. Let me show you. This code regresses the explanatory variable foreign against the dependent variable price. The regression results of this table are pretty easy to interpret, but before we do that, let's quickly look at some diagnostics. The regression includes 74 observations, so that's good. There are no missing observations. The F statistic is not significant. Here we are looking for values below 0.05. Values above 0.05 imply that our total model, in other words, all the variables in our ordinary least squares regression, do not explain how price varies. Likewise, the R-squared is extremely low. A value of 0.0024 means that we are explaining almost nothing in terms of price variation with the variable foreign. Now let's go and look at the results. We have one variable called foreign. However, this is a binary variable, not a continuous variable. Such variables have the following interpretation. If the value of the variable is flipped from 0 to 1, in other words, if a car changes from being a domestic car to a foreign car, by how much will the car's price increase? The answer here appears to be $312. However, we also observe that the standard error around this estimate is quite large. The standard error is $754. That means the associated t-statistic is below 1.96 and the p-value is above 0.05. This means this variable is not statistically significant at the 95% level. We get an idea of the uncertainty by looking at the confidence interval. This ranges between minus $1,200 and plus $1,800. So the true value is somewhere in there, but because the confidence interval crosses 0, we cannot claim statistical significance compared to the value 0. Finally, remember that the effect of a variable is conditional on other controls. In this case, there are no other variables in the model, but there is a constant, and the constant is the value of price if everything else is set to 0. In other words, if a car is domestic and its value of foreign is set to 0, it will cost $6,000. A foreign car is $312 more expensive, so it would cost around $6,300. We can also visualize this. Here we see the estimated effect of foreign cars on price. Domestic cars are cheaper on average and foreign cars more expensive by $312. But the confidence in of both values is so large that they are not statistically different. Great! Let's go ahead and increase the number of variables in our model. We could throw all our variables in and simply see what sticks. This is what a data mining approach would generally do. Stata has various data mining abilities, including stepwise regression that will automatically eliminate variables that are not statistically significant. However, there are some conceptual problems with this approach. One of the most important problems is that it prevents users from thinking about the problem at hand and doesn't allow them to understand how their data analysis
is related to underlying theory or their research hypotheses. For this demonstration, let's go ahead and slowly add one variable after another variable to our regression model. We will not remove foreign, even though it is insignificant, because the addition of other variables may change its effect. Let's go ahead and add miles per gallon to our model. We see now, interestingly, that some immediate significant changes have occurred. Our R-squared has jumped drastically to 0.28. The adjusted R-squared is a little bit lower at 0.26, but this is still much higher than before. Our new variable, miles per gallon, is statistically very significant with a small standard error and a high t-statistic. Each increase in 1 unit of miles per gallon, in other words, cars getting more fuel efficient, will decrease the car price by $294. However, we also see that the effect of foreign cars has increased dramatically to plus $1,700. The standard error has come down a bit, from previously 750 to now 700, and the variable is now statistically significantly different from 0. What a big difference one variable made to our model. Importantly, we can explain this change. It turns out that foreign cars have significantly higher miles per gallon numbers than domestic cars, and once this factor is controlled for, the actual price of foreign cars is higher than for domestic cars. This is because the effect of miles per gallon is negative on price, and because foreign cars have higher miles per gallon, their price was lower. Now that this effect has been controlled for, and therefore taken out of price, the actual effect of a car being foreign is that it causes a price rise. This is a perfect example of the exogeneity assumption I was talking about in the previous session. We omitted an important variable from the regression model, and the explanatory variable we did include was correlated with that important variable in the error term. So therefore, the previous result was biased. However, because we have now moved the offending variable, miles per gallon, from the error term into the regression model, we are controlling for it and hopefully produced a less biased estimate. This really shows the importance of careful model building. Let's go ahead and introduce a third variable to our model, weight. Weight is likely to be an important variable because heavier cars need more raw materials, but also because heavier cars are likely to affect the miles per gallon number, and we know that this in turn affects the foreign estimate. So let's go ahead and add it to our regression model. Look at that. Our R-squared jump up again by a large margin, and also our estimated effects have changed again. Let's explain it one more time from the top. The new variable weight is statistically significantly different from 0 due to its small standard error, high t-statistic, and small p-value. The effect is positive. In other words, each additional pound of weight on a car increases the price by $3.46. The effect of miles per gallon is now positive instead of negative. So the inclusion of weight reversed the sign of this estimate. Higher miles per gallon cars now lead to higher prices, although this effect is not statistically significant. This makes sense. After all, higher miles per gallon cars are more fuel efficient and save money. This may require better technology, and therefore such cars may cost more. However, the previous effect was masked by the fact that heavier cars had worse mileage. Now that this is controlled for, the effect of miles per gallon has become less biased. Moreover, because there is a knock-on effect of miles per gallon on foreign status, we see that the effect of foreign cars jumped to $3,600 with a lower standard error of 680. This is another important example of regression bias, where important explanatory variables
were left in the error term. Let's assume for a moment that we are now finished with our model building and that we are happy with the specification that we have. The next step is usually to perform some diagnostic statistics, especially in relation to the Gauss-Markov assumption discussed in the previous session. Unfortunately, the exogeneity assumption cannot be tested and can only be inferred via adding other variables to the model, as just shown, or by resorting to theory. We can, however, test the homoscedasticity assumption. So let's go ahead and do that. Here, Stater performed a test for homoscedasticity. The results show that the null hypothesis of a constant variance is rejected in favor of the alternative hypothesis of heteroscedasticity, in other words, varying variance. We can also explore this visually by examining the residuals. Here, we've plotted the residuals versus the fitted values. This residual versus fitted plot shows how the residuals are distributed around the plane of best fit. Values close to 0 mean a good fit. We can clearly see on this plot that when we move from low fitted values to higher fitted values of price, the variance of the residuals around 0 increases. This is clear evidence of changing variance and needs to be dealt with. We can either use robust standard errors or specify a different functional form that tries to remove this changing variance. Improving model fit is often a better first option, and in this case the problem might be caused by the fact that, like many price variables, car price has a long tail. Often we transform such variables with logs. So let's go ahead and do that. Now, let's run a new regression with the dependent variable as log price instead of price. And let's see what happens. At first glance, it looks like everything has changed. The coefficients are completely different. However, because we have now transformed the dependent variable, all explanatory variables relate to the log price and not the price. And this means their interpretation is slightly different. Now, a 1 unit increase in weight increases the log price of a car by 0.0004. This can be a rather inconvenient way to interpret our model estimates, so we often retransform the coefficients to make them easier to understand. When a regression model has no log transformation, either for the dependent variable or the explanatory variable, we call this a level model, and the interpretation is straightforward. When an explanatory variable is in logs, the interpretation on the coefficient changes to a 1% increase in x causes a beta divided by 100 unit change in y. When the model has a log dependent variable, the interpretation changes to a 1 unit change in x causes a beta times 100% change in y. And when the model is a log-log model, the interpretation is that a 1% change in x causes a beta percent change in y. So in this case, a 1 unit change in weight causes a 0.0004 times 100 equals to 0.04% increase in price. Likewise, foreign cars now cost around 53% more in terms of price. Now let's go back and test the homoscedasticity assumption again. The test statistic reveals that we can now accept the null hypothesis of homoscedasticity. We can also visualize this again using the residual versus fitted plot. Here we can see that as we move along the fitted price values, the spread of the residuals around the horizontal zero line is much more even. This is visual evidence that our model now has homoscedastic errors and that we can accept that particular assumption. Next, let's go check
for collinearity. This variance inflation factor test highlights to what extent each variable inflates the variance of the model. High values above, say 50 or so, on particular variables are indicative that these particular variables are collinear with other variables. Here, there is no evidence of high collinearity in our model because all variables have very low variance inflation factor values. Finally, we can also introduce more complicated functional forms. Parameters must be linear, but variables can be transformed and offer more complex forms than just linear relationships. For example, we can include a weight squared variable into the regression to allow a quadratic relationship to exist between log price and weight. In this new regression, data included weight and a weight squared variable. It is important that the interacted variables are analyzed together. So whilst the weight variable is not statistically significant, the squared weight variable is statistically significant, and a joint test should be done on both to see whether the pair is significant or not. Let's assume for a moment they are jointly significant. The interpretation of the output becomes a little bit more complicated, but interaction effects can also be visualized, and Stata can do that for us. Here we can see that the relationship from our predicted ordinary least squares model between weight and log price is not actually linear, but appears to be quadratic in nature. In other words, there is a curve going through the relationship between price and weight. As weight increases, the log price increases more and more and more. Great. Now let's assume we are done model building. Regression models are often not presented as they are shown by statistical programs. There is simply too much information in the tables presented by statistical programs, most of which is redundant or not useful to layman readers. It is also common to include multiple regression models in a table so that readers can follow the progress of the coefficients as additional variables are included or removed from models. Here's an example of how regression tables often look in reports. This here is a classical regression output table that contains the coefficient to 3 decimal places and standard errors to 3 decimal places. Asterisks are included to easily identify statistically significant effects, and the diagnostics only include the observation count and R-squared statistic. This table easily allows readers to read across and examine how the effect of the variable foreign on price, for example, changes as we change our model specification. This kind of approach is important as it is a transparent approach that shows the ingredients of how this particular statistical meal was made. Readers can judge for themselves if they agree with your particular conclusion or not. And this concludes this practical session on ordinary least squares regression.